Hello there, this is Mr. Smith with reading quiz number 8. This is about integration by parts. We've learned other integration techniques up until now, including U substitution, which undid the chain rule. And now we take a look at what happens when we want to undo the product rule. It's a little bit more complicated than what we did with substitution, but once you know the formula, then it's not too bad to apply. So let's take a look. What is integration by parts? Earlier we discovered the substitution method for finding antiderivatives, and it was the opposite of what we did with the chain rule. Now we look at this new technique, which is what we're going to use to undo the product rule. And basically when you're going to use this technique, when you see this, is if you have some sort of a product in your integrand and your integral, you're going to want to apply this formula. So for example, if you have e to the x times sine of x as your integrand, or if you have x cubed times e to the x, and those sort of things. When you have two distinct functions in your indefinite integral, this is a very useful formula. So let's take a look at what that formula actually is. The formula we use is the integral of f of x times g prime of x dx is equal to f of x times g of x minus the integral of g of x times f prime of x dx. That sounds like a mouthful, but usually we write it as the integral of u dv is equal to u times v minus the integral of v du. Notice that we've switched the integral of u dv with the integral of v du on either side of the formula. And notice too that u matches up with f of x, dv matches up with the g prime of x dx, and so forth. So where does this formula come from? Well, if we were to take the derivative of a product, f of x, g of x, then we would get f of x times g prime of x plus g of x times f prime of x. That's just the product rule. Now, going up a level, if we integrate, we would notice that f of x times g of x is equal to the integral of f of x times g prime of x dx plus the integral of g of x times f prime of x dx. And finally, moving this very last integral here, the integral of g of x times f prime of x dx, over to the left side, gets us the formula that we have above. So it's not too hard to remember. The integral of u dv equals uv minus v du, and usually we stick with that formula when we're doing these problems. So let's look at an example. Before we do that, actually, let's talk about the different ways that you could choose a u and choose a dv. And typically, when you see two different types of functions, you're going to make one type u and the other type will be dv. And the acronym LIPET, which is a weird acronym but will help us out, will help us choose what we want u to be. It's not something that we're going to use every single time, but it gives us a decent idea. L in the acronym LIPET stands for L. Choose logarithms first if available. All right, so if you see a natural log or a log function, then use that as your u. I, then you're going to choose inverse trig functions such as arcsine, arccosine, etc. P will be polynomials, E exponentials, and T are your regular trig functions like sine and cosine. So now let's take a look at an example. Let's say we want to find the integral of x cosine of x dx. Notice that there are two different types of functions in this. There's the x part, and then there's the cosine of x part. The x being like a polynomial, and the cosine being like a trig function. So if we go down our LIPET acronym, we see that we don't have a logarithm or inverse trig function, but we do have a polynomial. That's the x part. So what we do is we choose u equal to x. This means that dv gets everything else that's left, cosine of x times dx. So what you can do is you can set up a very useful chart of u, du, and v and dv. Again, just like we did with substitution, we're going to find our du by taking the derivative of u. And so in so doing, we get du is equal to dx. And then we have a dv equal to cosine of x dx. In order to find v, we just integrate, and we get sine of x. Now that everything's in our nice little chart, we apply our formula. We get the integral of u dv is equal to x times sine of x minus the integral of sine of x dx. Usually in this process, we're going to have an extra integral that we'll need to evaluate somehow. In this case, this is a pretty easy one to evaluate. The integral of negative sine of x dx would be cosine of x. And don't forget your plus c. So your final answer is x sine of x plus cosine of x plus c. As always, you can check your work by taking the derivative, and this derivative involves a product rule with the x sine of x part, hence this technique. When you do the product rule of x sine of x, you get sine of x plus x cosine of x, and then to get rid of that extra sine of x, that's why we have that cosine of x part as part of our antiderivative. That'll give us the minus sine of x that we need to cancel out to just get the x cosine of x part. Example 2, let's say we wanted to integrate x squared times e to the x dx. Okay, so notice that by our Lipit notation, the thing that comes up first is the polynomial, that's the x squared. All right, so we're going to choose our u equal to x squared. That means dv is equal to e to the x times dx, which is all the rest of it. I'm going to set up a useful chart of u du v dv. I didn't have enough space on the slide, so I just wrote them out. U is equal to x squared, du is equal to 2x dx. dv is that e to the x dx, and so the antiderivative of that would be e to the x. So now once we apply our formula, that uv minus v du part, we get x squared times e to the x minus 2x e to the x dx. Now notice that this is not an easy integral to find the antiderivative for. However, we are more than welcome to try to use integration by parts again, which we do. In this case, we've got another polynomial, so we let that equal to u, 2x. du then is 2 dx. dv again is e to the x dx, and v is e to the x, v being the antiderivative of dv. Now we apply our formula once more. X squared times e to the x minus 2x e to the x minus the integral of 2 e to the x dx. Be very careful, make sure that you put parentheses around this entire evaluation of the integral, because you don't want to lose one of your negatives. When you finish this out, you get x squared e to the x minus, in parentheses, 2x e to the x minus 2 e to the x. We finally got down to an integral that's easy to find the antiderivative for. And distributing our negative, we get x squared e to the x minus 2x e to the x plus 2 e to the x plus c. And you can, again, always check your work by taking the derivative, and you'll see that a lot of the terms cancel out, so we're just left with that x squared e to the x part. Example 3, the integral of natural log of x dx. Now, integration by parts is useful in situations other than just the situations where you have two different functions. One way that you might want to think of this is that dx, or 1 dx, serves as a polynomial. So by our Lipit, we might choose, in this case, u equal to natural log of x, because that's the L part for logarithms. That means that dv is just that leftover dx part. Okay, so when we set up our chart, we've got u equal to natural log of x, dv equal to dx, du is dx over x, and v is x. All right, so it's the same as what we did before. When we apply the formula, we get x natural log of x minus the integral of dx over x times x. And you notice that the x's cancel out, and so you're just left with dx. When you integrate dx, you're just left with x. So your final answer is x natural log of x minus x plus c. Again, check by taking the derivative, and by the product rule, you get things to cancel out, which is just what we wanted. And you're just left with the natural log of x part. So you can see that this is very useful even when you don't see an apparent product. All right, a little bit more complicated one, the integral of x cubed sine of x dx. If you remember just a minute ago, we did x squared e to the x dx, and we had to do the integration by parts twice. Well, let me show you a trick that'll make that faster. This is what's called tabular integration, and it'll be your new friend. You can't use it all the time, but you will find it very useful most of the time. So when you have larger polynomials as part of your integrand, tabular integration is helpful in just organizing your thoughts. All right, you're going to put the u, generally the polynomial on the left side, which is x cubed and all of its derivatives, and dv and its antiderivatives on the right side. So we're going to start with sine of x, go up to negative cosine of x, and so forth. And you're going to go until you reach 0 on the left. On the next slide, you'll see what we're going to do with that. The derivatives are on the left, all right, and the antiderivatives are on the right. And what you want to do is you want to draw a diagonal between the first row of derivatives and the second row of antiderivatives, and then continue on with alternating rows there. You're also going to alternate the sign, and I'll tell you what that sign means in a minute. The first arrow gets a plus, second arrow gets a minus, third arrow gets a plus, fourth arrow gets a minus. So what you're going to do is you're going to match the derivative with their antiderivative diagonally across but one row down, as indicated above. That's the tabular part. We're writing this in a table. Again, the signs alternate from plus to minus, and we're going to put it all together by multiplying. X cubed times negative cosine of x minus 3x squared times negative sine of x plus 6x times cosine of x minus 6x sine of x plus c. And you notice, bam, we're done. All we had to do was organize our thoughts in a way that made this easy. The reason why the signs alternate, by the way, is because of that negative sign in our formula. Remember, it's uv minus v du, or the integral of v du, rather. And the signs are alternating because first time around we're going to have a negative v du, and then it becomes a negative of the negative of v du, and so that turns into a positive. And in that way the signs alternate. So we could have done this with example 2 when we had x squared e to the x dx and wanted to find that antiderivative. Notice I put my u of x squared on the left, and then all of its derivatives follow. And then the antiderivative of e to the x, which is just e to the x in all circumstances. Draw an arrow going from the top row to the second row, from the second row to the third row, and so on, and then alternate your signs. So we match our derivative with the antiderivative diagonally, as indicated above. The signs alternate, and we get x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Pretty cool. Well, sort of. You can't always use this tabular integration on your product rule problems. And the problem is, if you have a function whose derivatives don't go away necessarily. For example, the integral of e to the x sine of x dx. In this case, we're going to choose our u and dv carefully according to Lipit. Our u is going to be e to the x, our dv is sine of x dx, du is e to the x dx, and v is negative cosine of x. When we apply our formula, we get negative e to the x cosine of x minus the integral of negative e to the x cosine of x. This doesn't appear like it's helped very much, even when we simplify it a little bit. So we seem to have a more complicated integral. But what happens if we just try integration by parts again, with just the e to the x cosine of x dx part? And when we do that, we get u is equal to e to the x, dv is equal to cosine of x dx, and then v becomes sine of x, which is pretty neat, actually. When we actually apply the formula, we get the original integral of e to the x cosine of x is equal to e to the x sine of x minus the integral of e to the x sine of x dx. And we can substitute in what we just got, the e to the x sine of x minus e to the x sine of x dx. Well, the cool thing about that is the original integral we wanted is that e to the x sine of x dx integral. So we can just move that integral over. We get 2 of those, the integral of e to the x sine of x dx. And when we divide by 2, we get our antiderivative. So we couldn't use tabular on that, but the cycle of the sine function allowed us to come back to something that we could use. Finally, we need to discuss what to do when we encounter a definite integral that requires integration by parts. So our formula is the integral from a to b of u dv is equal to uv, evaluated from b to a, minus the integral from a to b of v du. That's a typo there. So for example, if we want to evaluate the integral from 0 to 2 of x times e to the x dx, we use our formula. We plug in just as before, and we'll have to actually evaluate the integral from 0 to 2 of e to the x dx. Similarly, you'll see a lot of these chart questions on the AP exam where u of 3 is 7, u of 5 is 2, v of 3 is negative 1, v of 5 is 6, and you know something about an integral. Find the integral from 3 to 5 of u dv. And the answer is done very similar, just make sure that you apply your formula. For example, we need to do u times v from 3 to 5 minus the integral of 3 to 5 of v du. We plug in the numbers that we know from above, and we solve.